Hi everyone, welcome back to the video walkthrough of question number 2 Red Herring of the week 6 worksheet. So this question is asking you to give a tight asymptotic bound for red herring as a function of n. And we just take the length of the input array as our input of the asymptotic. And if possible, just give a theta bound for the overall runtime. Otherwise, provide a theta bound for both the best case and worst case runtime. So let's start with understanding what the red herring function is trying to do. So we first have a if statement to check whether the length of array is less than 1 or whether the length of the first row of array is less than or equal to 4. If that's the case, we will return 0 immediately. If that is not the case, we will keep iterating through all the elements of the 2D array. So we have a nested for loop. The first 4 statements is trying to iterate through each row of the 2D array. And the inner for loop is trying to iterate through all the elements of the row we are at. For example, the row I we are at. And if we are, and we just keep illustrating the elements of the specific row. If we iterate the fifth element of the row or the element with index of 4, we will just return -1 immediately. And if the row has fewer than 5 elements, we will just keep iterating through all the rest rows. And if every row is the size of every row is less than 5, we will just return 1 eventually. So since we take the length of the input array as the input n, so remember that we always think about an infinity, we always think about n approaches infinity as the condition of our runtime analysis. So for here, we're just trying to think about if there is a 2D array with infinite rows and infinite columns, what will happen? So at that case, we should always have a fifth element of each row. So the function will return once it reaches the fourth element of the first row and the fifth element of the first row of the array matrix. And if it reaches this element, it will just always it will always return -1 immediately. And in that case, the function will always take constant time. So the best case is always equal to the worst case, which is just constant time. And we just express it as big theta of 1. And this is analysis of question number 2.